chemistry students run an experiment to measure how temperature affects their final chemical yield, they gather pairs of physical data. They record the heat of the room, and they record the exact amount of product they get at the end. As humans collect this information, our brains naturally try to connect the dots. This animated graph plots that lab data, with temperature on the x-axis and percent yield on the y-axis. Almost immediately, you can eyeball the cluster of dots and draw a straight line right through the middle to spot the upward trend. But a computer cannot rely on human intuition. To a machine, that single line you just imagined is competing against dozens of other ways a straight line could theoretically cut through those exact same coordinates. The machine needs a concrete mathematical rule to determine the truest line out of infinite possibilities. The algorithm that solves this dilemma is called linear regression. It acts as the mathematical baseline for measuring how much one specific piece of evidence influences a final conclusion. To find that perfect line, the algorithm relies on a rigid rulebook from classical algebra, the equation y equals mx plus b. In machine learning contexts, this is often expressed as y hat equals w transpose x. In this framework, x is the independent input we know, like the temperature in the laboratory, and y is the output, or the final value we predict, such as the chemical yield. The most critical part of this equation is the slope, or the weight. The weight tells the machine exactly how much a single unit of change in our input shifts the final prediction. If the weight is a large positive number, a tiny bump in temperature causes a massive spike in yield. But the machine has to test its weights, and it often starts with a bad guess. This scatterplot shows a poorly fitting line cutting through the data. Notice the vertical lines stretching from the raw data points to the main prediction line. Statisticians call these gaps residuals. They represent the physical distance between what the model predicted and the actual observed reality. To evaluate how bad this guess is, the algorithm uses a method called ordinary least squares. It takes the distance of every single residual error and draws a literal square out of it. Squaring the numbers severely penalizes massive errors, giving heavy mathematical weight to the data points that fall furthest from the line. Now, the machine simply hunts for the minimum. It physically shifts and pivots the main prediction line until the total combined area of all those individual squares reaches its absolute lowest possible value. Executing this mathematical optimization is how data scientists lock in a standardized baseline for their predictions. That perfect math works flawlessly when the variables cooperate. But real-world data is chaotic, and it rarely behaves the way we want it to. This scatterplot shows a dataset naturally arranged in a deep U-shape. A common mistake is forcing a perfectly straight regression line onto data that naturally curves. Blindly applying the algorithm here is a disaster. The line cuts straight through empty space, generating massive residual errors on the ends and the middle. This is what we call an estimation bias problem. In this context, bias is the systematic error that occurs when you try to approximate a complex curved reality with a model that is too simple. Because this model is built to only see straight lines, it is biased toward a simplified answer that doesn't exist in the actual data. There is an even more insidious failure point hidden in the math. Sometimes a perfectly straight line actively hides the truth about the underlying populations we are studying. This phenomenon is called Simpson's paradox. Here is a scatter plot showing a large aggregated cloud of data. The regression line for the total population shows a clear positive correlation, but this is an illusion caused by aggregation bias. When we separate the data by subgroups, the unified cloud splits. The actual trend for every individual population goes in the exact opposite direction. Data scientists can fix these rigid failures. They can apply basis functions to square or transform the inputs, allowing the rigid line to bend and warp to match the data's true shape. Ultimately, the value of linear regression is its rigidity. It allows researchers to strip away noise and calculate exactly how much one variable influences another, provided the evidence follows a straight path. But what happens when our formula's core assumption breaks down entirely? What do we do when our inputs secretly start influencing each other? We'll solve that in the next episode.